So now we have Markovnikov's addition and then the anti-Markovnikov addition. Two things to keep up with. But as I said before, it's nice to be able to have the option of directing that bromine in one direction or the other. One limitation to this anti-Markovnikov is that it only works with HBr. If you're using the chloride, other halogens, you always get Markovnikov addition. And so with HBr, we have to be told clearly, are there peroxides or not, and that would be stated so that you would know which possibility you're looking at. In the absence of words like peroxides or an indication of, again, ultraviolet light, then we assume it is the normal reaction. Well, Markovnikov's addition can be understood in terms of carbocations forming. Anti-Markovnikov additions can be understood in terms of radicals and their stability. And we've seen radical reactions back in Chapter 4 as well. Radicals typically don't have a positive or negative charge. They are neutral, but they feature unpaired electrons, and so they are unstable in the same way that carbocations are unstable. But they do exist for some period of time, and they're the key to figuring out what products that we make. So with this anti-Markovnikov addition, what we get are radicals of bromine atoms. And that bromine atom can add across the double bond. Again, one of the bonds from the double bond makes a covalent bond to bromine, and that's going to leave an unpaired electron on the carbon next door. And so here are the two possible radicals, or here's one of the two possible radicals we can make, and we would expect this one to be more stable because it's a secondary radical. If the bromine had ended up on the second carbon and the radical, the unpaired electron, on the first, it would be less stable. So just as we tend to make the most stable carbocations, we also tend to see with reactions that involve radicals, they want to make the most stable carbon radicals. And so this is the key difference between this mechanism and what we saw before. In the regular Markovnikov, we had hydrogen and a positive charge that were the new features of the molecule. Here the bromine, the halogen's coming in first. And then in a subsequent step, a hydrogen makes a bond where that radical is, and so we get a stable molecule, but the bromine ends up in just the opposite orientation of where it would be if there were no radicals at all. And in fact, in real life, one has to be meticulous to keep sources of radicals out of the reaction flask so that we don't accidentally get an anti-Markovnikov addition if we don't want one. With HBr, again, it can go either way. So oftentimes, if we want the normal addition, we do these reactions in the dark so there's no stray ultraviolet light, and we make sure that we don't accidentally have even a speck of peroxides or anything that can create radicals. But again, it's only the bromide that has this variation. Chlorides always are normal Markovnikov. Iodides always the normal Markovnikov. Well, let's talk a little bit about hydration. That's adding the elements to make water across a double bond. And you can see here the recipe is an acid like sulfuric acid and water itself. So these are fairly concentrated solutions of sulfuric acid. We do need an acid to make hydration work, but we don't want to use like HCl or HBr because, as we've just seen, we'll get the halogen in our product. But here the intention is to make an alcohol. So we've got a solvent that has got a lot of water in it, but we again need some source of hydrogen ions. H2SO4 is great at being an acid, but it does not have any tendency for the sulfate to behave like a nucleophile, at least not at these concentrations. And so, as it says here, this follows the Markovnikov rule, and we get the OH group where we would expect if we follow the rule that the incoming hydrogen goes to the carbon that already has the most hydrogens. And again, for the ring compounds, you can mentally add in hydrogens when you're doing problems like this to be sure of where the hydrogens are in the first place.